All right, guys, I assume it is rainy weather, and in rainy weather, people have such low tolerance of mathematics. I guess mathematics is like swimming pool. People do not go into the swimming pool when it's raining. Strange. So before we continue with anything, guys, again, please turn on your cameras if you're not in a very uncomfortable position. Thank you. As many of you as possible, guys, so that I may know who you are. And the first order of the day is to discuss that one problem that we left behind from Monday's class. It's not an easy problem, and I hope some of you have had a chance to think about it. How many of you have thought about this problem? Impressive. 0 is my favorite number. So you have n antennas, of which m are defective and n minus m are functional. Defective antennas will be indistinguishable from one another, and active antennas are indistinguishable from one another. The system functions as long as no two defectives are next to each other. You understand? So here is how you might solve this problem. So imagine that the functional antennas are designated with 1. And here we place 1s. Now, between the 1s in front of this first one and after the first one, and basically between any of them, there is space. Do you agree? There are spaces. So how many spaces are there? If they are n minus m functional antennas, then we have a first space before the first antenna, second space before the second antenna, all the way until we reach to the n minus mth place before the last functional antenna, and one more space. So in total, there are n minus m plus 1 spaces. Yes? Now, out of those spaces, we choose the spaces that will be occupied by a defective antenna marked by 0. There are m defective antennas. So do you see? We have now distinct spaces that we can choose. So this is space 0, space 1, space, so yes, all the way to space n minus m. So altogether n minus m plus 1 spaces. Or you can call it whichever label you would like that. So the trick here is that although antennas are indistinguishable, in other words, functional antennas are indistinguishable and defective antennas are indistinguishable, we can nonetheless distinguish the spaces between the functional antennas. And we have n minus m plus 1 spaces, here it's marked. And out of those spaces, we need to choose m spaces to be occupied by the defective antennas. Yes? So they are n minus m plus 1, choose m functional arrangements for the system. Clear? Any questions before I move on? Fine. Then we go on to multinomial coefficients. And here is the legend. So we have 3 dragons, and each has kidnapped a princess. 10 brave knights are sent to rescue them. 3 knights are sent to the first dragon, 3 to the second dragon, and 4 to the last dragon, you can see. The dragons will eat all those knights. The question is, of course, how many choices are there to send knights to the dragons? In other words, which of the 10 knights go to dragon 1, which of them go to dragon 2, which go to dragon number 3? And we can solve this problem as follows. Because the knights will be eaten, we can imagine that they are served on a plate. Do you see the black plate labeled 1 will have to contain 3 knights. The red plate labeled 2 contains 3 knights, and the last blue plate has to contain 4 knights. You see? So what we do, we are assigning destinies to distinct objects. In other words, we are assigning distinct destinies to distinct objects. The destinies are the dragons, and the objects are the knights. Yes, I often think about the train going, sending Russian soldiers to war, and with the words, "Goodbye, Moscow, your soul will remain with us." There is a line in that song that I really like. It says that we chose our destinies for ourselves. So that's kind of what I think of. That's why I have this picture here. Okay, so the first trait, basically this black crate is destined to go to dragon number 1, and those are the knights to be placed there. Second crate is destined to go to dragon 2, and third crate is destined to go to dragon 3. You understand? So this tells us what we should do. If I arrange all the 10 knights, there are 10 factorial arrangements. Yes? Of those arrangements, you can move around knights in the first plate without changing anything, move the knights in the second plate without changing anything, and move the knights in the third plate without changing a single thing. So altogether, they are 3 factorial, 3 factorial, 4 factorial rearrangements that do not change anything, which means that the possible destinies here are 10, choose 3, 3, and 4. This is the multinomial coefficient. So it's 10 factorial over 3 factorial, 3 factorial, 4 factorial. Have you understood the explanation so far, guys? Because it's going to be very important. Do you see what we are counting? We are imagining each knight is an individual. So there is a distinction between knight 1 and knight 2. They are different people. And there is a distinction between their destinies. Yes, in a few moments, I will give you examples, and I will ask you if you understood what in that example is analogous to the knights and what is to their destinies, to the dragons. Okay. So in general, if we have R distinct destinies and N objects, distinct objects, where destiny number 1 requires N1 objects, destiny number 2 requires N2 objects, and so forth, where, of course, the sum of the objects for each destiny equals the total number of objects to be distributed. Then this multinomial coefficient is the same as N factorial divided by N1 factorial and 2 factorial all the way to N sub R factorial. So this immediately allows us to, for instance, understand what happens when we expand a multinomial coefficient. Remember, we did the same thing when we had x1 plus x2 to the power of n. That was last lecture. In this lecture, we just generalize it. The formula isn't as nice, but you can imagine what will happen in the situation. Now, if I multiply those parentheses, then we have parentheses 1, parentheses 2, all the way to parentheses n. And each parenthesis will contribute 1x, either x1 or x2 or xm, right? So that would be what goes in here. Then from second parenthesis, what goes in here. And the last parenthesis is the end parenthesis, what it contributes. So when you expand multiplication, it's the same as picking an outcome from each parenthesis. Yes? And placing it over here. Good? So first question is, how many additions is in the above sum without simplification? If I do not simplify anything, but I just combine each term from each parenthesis and add, how many summons do I have? You understood my question, guys?
4.
Well, we are doing it in general, where the power is n and the number of terms added is n. right? So it's x1 to xn. So it has to be in terms of
N.
m and n, your answer.
Yeah, N summons.
Okay, so one person is saying, I think two people, one person wrote it and some say n summons. Any other ideas, guys? You see what happens. It's multiplication is every term from here basically, with every term from here, with every term from anything in between. You follow? If you remember the lecture, guys, and you're not rusty from Monday, you remember we talked about the binomial theorem, correct? So this is exactly that same situation. So how many possibilities are there? Okay, Gustavo, interesting. But again, there is M and N. So maybe you mistyped. Okay. Good. A few people answered this to be n to the power of n. This is basic principle of counting. There will be a match with 1x from the first parenthesis, right? So that has m possibilities. The second parenthesis can contribute additional m possibilities, and the next is additional m possibilities until the last one contributes m possibilities. So it is by principle of counting, m times m times m times m, m to the power of n is the right answer. Just to remind you quickly, here was the situation with let's say x1, x2 with binomial theorem, and I will just make it squared so I don't have to write too much. Yes. What is that situation, guys? That's x1 plus x2, first parenthesis, x1 plus x2, second parenthesis. You agree? And then what you observe when you expand multiplication is that you will see x1 matched against x1. That means x1 from first parenthesis matched against x1 from second parenthesis, plus x1 from first parenthesis matched against x2 from second parenthesis, plus now x2 matched against x1, plus x2 matched against x2. Do you see? Here we had m equal to 2 and n equal to 2. What do we get? We get we got 2 squared matches. You understand? Yes. Very good. Now, if you understood, guys, and that's an important question here, right? In this example, right, you see what happens when we expand, and this is a bit, this is just a test if you comprehend the analogy of dragons and knights. In this example, do you think who are the dragons and who are the knights in the expansion of x1 plus x2 squared? How many dragons do I have? How many knights? And which is which? Maybe so that you don't answer it with this question and there is some sort of possibility here. Let's say, what about x1 plus x2? And we place it to the cube power. And my question is, who are the knights? And who are the dragons? Yes, they are equal, Gustavo, but in terms of combinatorics, when we're understanding how parentheses are expanded, it's useful to remember from which parentheses they came. right? So x1, x2 means x1 came from first parenthesis, x2 from second parenthesis, whereas x2, x1 means the reverse. Good. So this is a slightly difficult question, but let's see if you are comprehending it. Who are the knights in this example, and who are the dragons? And you remember, in my analogy, the knights are the distinct objects that are assigned distinct destinies. Okay. So in this case, what is destiny and what is knight? Well, James, 3 is a number, right? So a number counts objects. Yes, you can tell that you are not listening to Russian poetry. Here is the way I would have answered. So the parentheses are knights, right? And x1, x2, x3, dragons. Now, why is that the situation? Look at it, guys. What happens when I expand the parentheses x1 plus x2 cubed, right? What happens there is, this is x1 plus x2, first parenthesis, x1 plus x2, second parenthesis, x1 plus x2, third parenthesis, yes? Now, when I when I have this summation, I then have, in this case, 3 boxes, right? This is for first parenthesis, second parenthesis, and third parenthesis. So for instance, if I make x1 equal to x2, and the second box I fill with x2, and the last one I fill with x1, what does it mean? It means parenthesis 1 was assigned, this parenthesis was assigned to x1. Parenthesis 2 was assigned to x2 here. This is, sorry, parenthesis 1 assigned to x2, parenthesis 2 is assigned to x2, and parenthesis 3 is assigned to x1. Right, so there are 2 dragons, dragon x1 and dragon x2. And when we have those boxes, then we have a situation where each parenthesis is assigned to go to x1 or to x2. Okay. So that is very useful in understanding what's the coefficient, right? If I asked for the coefficient where the power of x1 is n1, the power of x2 is n2, the power of x3 is n3, and so on, where the sum of the coefficients is clearly equal to n. Here you have it, right? The summation is over all such possible sums. They are not easy to list, not like in the binomial case, where if I know how many went to x1, I right away know how many went to x2. Here it's a bit more complicated, but nonetheless, you can condense the summation by just grouping on the number of x1s, x2s, and all the way to xm that you have. Okay, so this means what? This means that out of n parentheses, and 1 were assigned to contribute x1, and 2 were assigned to contribute x2, and so forth. Good. So that's how you get that multinomial coefficient. Let's try the following example, guys. Example A, and we will take a little bit of a pause to see that you understand it. You have very stone faces, and then I think I'm probably talking to myself. 9 pupils are divided into 3 teams, each consisting of 3 players. If one team will wear a red shirt, another blue shirt, and the last green shirt, how many outcomes are possible? You understand? So before you answer this question, guys, tell me if you understood my analogy, who are the knights and who are the dragons in this example. So write something like knights dash what it is, and dragons dash what it is in the comment section, please, and then solve the problem. All right, a few of you have responded. So I would have said the knights are obviously the players, and the dragons are the jersey, right? Red dragon is red jersey, green dragon is the green jersey, whatnot, right? So in this case, each jersey has to eat exactly 3 knights. Okay, guys, so now tell me, what do you think is the answer for A? And we will also write a Kafka protocol for it. Just write a formula for the answer, okay? I don't need the number. I just would like to see a formula for the answer. Okay. Barry, you forgot the 3 factorial. Very good, Chiara. Wonderful. Albert, you forgot a 3 factorial, but otherwise you're good. So here is the Kafka protocol. Okay, guys, the Kafka protocol will write in order. Within the red box, the numbers have to be in order. So pupils are numbered 1 through 9, and the pupils assigned to the red jersey are marked in order from smallest to largest. So for instance, pupil 2, pupil 5, pupil 3 going to red means I have to write the code 2, 3, 5 in here. Yes, I have to write them in order. Like, this is not good enough because 2 has to be followed by a larger number, and this must be followed in turn by a larger number. Yes, so each team gets a shirt, right? So the blue team, here is the code for the blue team, and the green team, here is the code for the green team. Yes? Yes, you see, guys? So how many, basically, why do we have this 9 factorial divided by 3 factorial, 3 factorial, 3 factorial? That's because you see that 9 factorial is suggesting ordered selection, right? If I place the numbers 1 through 9 in this box, right? 3 numbers go here, 3 go here, 3 go here. That will definitely indicate which individuals were selected to which jersey, but it indicates more than that, because you see, if I have 1, 2, 3, or 2, 1, 3, or right, or any reordering of 1, 2, 3, it still indicates that players 1 through 3 were selected. Yes. So the codes are producing too many synonyms. They're describing the same situation in too many words. Good. So that's why I divide by, basically I just count how many rearrangements. So now in my analogy, if you like or understand it, I think of it as stacks of paper, because each meaning has exactly the same number of codes assigned to it, right? Each particular meaning has 3 factorial, 3 factorial, 3 factorial words assigned to it. So then you take number of words divided by number of synonyms equals to number of meanings. I hope it's clear, guys. I know it's might sound who knows how, but it's far clearer than what I say. So here is a slight modification, guys, and here you would have to think what happens. Yes. So only red shirts arrived. So there would be a jersey assigned to the red players, but blue and green players will not be assigned a distinguishable shirt, right? So you only can tell here is a red team, and here is some team that I don't know if it's green or blue, and here is another team I also don't know if it's green or blue. Yes? And it doesn't matter anymore. All that matters is that, you know, they are kind of sad, but they have this American spirit. All that matters is we are a team. Yes? So how many possibilities are there? So Gustavo says 9 factorial over 6 factorial. You see, guys, so here is Ryder and Gustavo. You have not made a Kafka protocol for which you receive a ticket, right? When you do not explain how you, I mean, I know based on your answer that you must have not produced a Kafka protocol, right? I can look at it and I think, okay, you decided to take the green and blue team and merge them into one super team of 6 players. That's not what I said. There are 3, 3, and 3, right? Teams. It's just some of them do not get a jersey. Right? So let's see what happens. We can use, guys, that same Kafka protocol, but we now strike away blue and green, which means I can take, all that I can tell, guys, is the red shirted people, but I cannot distinguish the destiny to go to the green dragon from the destiny to go to the blue dragon. Do you understand? So red, blue, green, because I'm colorblind in terms of green and blue. Red, blue, green looks to me exactly the same as red, green, blue. Yes, which means those 2 boxes I can move around, which means that even after I make that reduction from before, which is 9 factorial over 3 factorial cubed, I still have to make further reduction by readjusting, moving around those last 2 boxes. They can be moved around and the code is still producing the same result. You agree? So I must divide that result of the previous Kafka protocol that I already obtained by 2. Do you see that? Here I try to indicate that I no longer am aware of the blue part of the code or the green part of the code. You see what happens here? This part stays on the left, but I can permute the middle part with the last part. So this is the same as this. Got it, guys? That's why I advise you to be bureaucratic, right? Be very bureaucratic as you're learning to navigate your new life here, your new normal. You have to be very bureaucratic. Good? And guys, show me your faces. I know I'm creepy, but you know, I actually saw in a museum a very creepy looking dinosaur. I just the dinosaur looks to me like some old pervert that has to be arrested. Very weird. I can show you a picture. Which part? The code. Here we go, guys. Again, blue and green. The blue and green categories cannot be distinguished, but what can be distinguished about people in the blue category? That they are in one team, and the people in the green category, they are in one team. Yes? Beautiful. So you see here in previous part of the problem, I was aware of red, blue, and green. Now blue and green are the same color. So this code and that code are the same, which means the answer is just like in part A, with the additional possibility of moving middle and last block. I can move them around. There are two possibilities for moving middle and last block. You understand? Yes, guys? And don't worry, you can ask many times. I will do my best to explain, especially in office hours. I can explain it and just wait for you to ask question after question, okay? You just have to imagine the codes. You see, guys, what do I imagine? I try to tell you what I see. I see stacks of papers, yes? And I mean, I first imagine having this 9 factorial stack of papers arranged into 3 factorial cubed piles, so 6 cubed piles. It's a big pile. And then I imagine when I made the code that I can compress them and I make one document. And then on that document, I see codes written in order, right? So I see something like 235, 149, 6, 7, 8. You can imagine that, yes? You imagine I see that code, so I always see them in each box, first box, second box, third box, relative to each of the 3 boxes. The codes are arranged from smallest to largest number, right? You can see that that's why I wrote those codes, right? You can see that this code has nothing to do in terms of this code. They're completely independent, but the red numbers are ordered, the blue numbers are ordered, and the green numbers are ordered. Yes. Now, since there is no distinction between middle and last, I see that this document is still overcounting. Now, how much is it overcounting? Twice exactly, right? Because for any block, any middle block and last block, I can find the reverse of middle block and last block. And that gives me the same exact outcome because it's still the team. I don't know who gets the green shirt anymore, right? So now I further staple 2 documents, right? So I now further divide by 2. Do you see why it came around? And if you understand, yes, so that's why it's over 2 precisely. Barry, amazing, right? So it's that number divided by, well, it's 9 factorial over what you said divided by 2. Yes. You can just say 3 factorial cubed. It's easy. 6 cubed easier than just what you wrote. And then maybe one more comprehension check, guys, right? So now no shirts arrived at all. So there are no jerseys whatsoever. We don't know who is red, who is blue, and who is green. How many possibilities now? And be very careful, guys. Again, be mindful. You know this game, guys. How many arrangements are possible when I move 3 objects around? There's first, middle, and third. How many rearrangements are possible? Just 3 rearrangements? We have first box. So first place is either red, green, or blue. 3 possibilities. Second place, once I pick this place, there are 2 possibilities for second place and 1 possibility for the last place. Yes? Good. Which means what? Which means that there are an extra 3 factorial. Good Gustavo and good other people that I've seen write not 3, but 3 factorial on the bottom. Yes? So that's the answer. It's 9 factorial over 3 factorial to the 4th power. Are you understanding? Because now, guys, there is no distinction. You see what just happened here? We still have 9 distinct objects, but we no longer have distinct outcomes, right? The only thing that is distinct is which individuals are together, but not what's their destiny. Destiny was eliminated from the conversation. Now we go to the next lecture, guys. Before I move on, I should have asked again. I'm sorry, I'm moving very fast. In previous classes, I spent a long time waiting for the students to respond. And I tend to run out of time as I get to the end of the semester. So I'm now rushing things a bit more. But if you have questions, you can stop me. Do you have any questions? Okay, good. Here is the next problem. Okay, so now we call it distributing identical objects among non-identical destinies. You understand what I mean, right? So before we had each object was different from each other object. The knights are individuals and their destinies are individual destiny. Yes, each goes his own way. Now here we try to understand a slightly different problem. How do we take identical objects, in other words, like matches, right? One match, another match, a third match, right? And how do I distribute those identical things? I cannot tell apart a match from another match, right? How do I send those identical objects among distinct destinies? Yes. So to make it clear, that problem was written when the situation in which we find ourselves is begun. 5 toilet paper rolls to be divided among 6 hypochondriacs. How many partitions are possible? Yes, remember the toilet paper crisis. So here is a question that it inspired me immediately to ask. When there are few toilet papers and too many hypochondriacs, what do we do? So here is right away a solution, guys. So suppose that x1 is the number of toilet papers that hypochondriac number 1 gets, x2 is the same for hypochondriac 2, and so on. If I see the units of toilet paper that each of them got and I add them together, I get 5. Yes. So from a mathematical point of view, we are counting integer solutions to this equation. Yes, we have 6 variables. Each variable can contain numbers from 0 to 5. And the sum of those variables has to equal to 5. How many possibilities are there? Yes. Now, I'm not sure if you still go to stores, but you have seen this, in a supermarket, you have this escalator, or what you call it. You have this treadmill running. What's the word for it? I forget it. You know what I mean, right? You have this when you place items on this moving. It has a word which I now can't remember. Conveyor belt. Thank you so much, Gustavo. Exactly, right? I'm losing my mind. So the conveyor belt is moving items around, and on the conveyor belt, what do you do to differentiate who gets what? You place bars. Do you agree? You place bars. So we can imagine that all the hypochondriacs place their items on the conveyor belt, and from the top, this might be the picture that you get. The black parts are the bars, and the circles represent toilet paper rolls, right? So you can imagine a view from above, like from a video camera, you're watching the conveyor belt. Yes. Now, based on this conveyor belt, you can see this is the start of the conveyor belt. That's the toilet paper rolls that person number 1 gets. Now, that's between nothing and the first bar. Between the first bar and the second bar, that's the amount of items that second person gets. Yes. You understand? So we are producing. Do you understand how to read this code? So we produce like a code from zeros and ones, right? Like you have this barcode, right? It's a barcode here, and the barcode uniquely determines who gets how many items. Do you agree? If I read this barcode as 0011000111, I know what each person got, right? Because I can just look at this code and I interpret. Okay. 00 means person, and then 1 means first person got 2 toilet paper rolls, and then followed by 1 means the second person got 0, the next person got 3, the next 0, the next 0, and the last 0. Yes. Amazing. And you agree that the barcode tells me the full picture. If I read the barcode, I know just exactly who gets what. Is that correct, Grant? Yes. So now observe, guys, that just like in the antenna problem, we can actually easily count how many positions there are for the bars, right? Because look what we do here. We have spaces. How many spaces do we have altogether? You see? So look at this code, guys. This code consists of how many zeros? Consists of 5 zeros because each zero represents a toilet paper roll. Yes. And how many bars? The number of bars must be one less than the number of customers. So the number of bars, we have 6 customers, so the number of bars has to be 5. Do you see why 5, guys? Because 1 bar partitions items into 2 categories, 2 bars partition the items into 3 categories, and therefore 5 bars will partition items into 6 categories. Are you with me? Very nice. And so what we just decide, I mean, is just where to place either the bars or the toilet paper rolls. Agreed? So they are altogether 5 plus 5 spaces. 5 of those spaces are occupied by toilet paper rolls and the other 5 by the bars. 5 plus 5 spaces. Out of those spaces, I need to choose 5 spaces for the either toilet paper rolls or for the bars, whichever you prefer to look at. Because as soon as I know the places of toilet paper rolls, the rest of the spaces are bars. Yes? You understand what I do, guys? Instead of looking at the toilet paper rolls, I look at the spaces, right? This is space 1, 2, 3, 4, 5, you know, right? So there are 10 spaces. Here it is, 5 plus 5. And 5 spaces are given, I just did it this way, right? 5 spaces are assigned the destiny of going to toilet papers and the other 5 to bars. So it's 10 choose 5 or 10 choose 5, 5 if you use multinomial notation. You agree? Because out of the 10 spaces, 5 go to become toilet paper rolls, the spaces go to become toilet paper rolls, and the other 5 spaces go to become bars. Again, let me ask you this one more question. In this example, the knights are what? And the destinies are what? How many destinies do we have? How many knights do we have? And what is what? Please write in the comments. No, Ryder. Knights are the things assigned. Destinies are the assignment. The dragon is your destiny, your assignment. What is assigned? What's the assignment? No, because in the analogy of that knights and dragons, the items must be distinct, the destinies must be distinct. Toilet papers are not distinct. No, so so you're getting closer, at least partially correct answers, but I don't see the right answer. No, And besides, guys, besides trying to guess nights and destinies, tell me the quality. Nights, they are what here? Right? So we have, again, this is what happened when we translated this problem. We had a conveyor belt, and we have the items. The items are either toilet papers or bars, either zeros or ones, listed on the conveyor belt. What is what? Okay, so so what was assigned? What did we assign when we created this barcode? Well, the nights are the 10 spaces, right? So we have space 1. Is space 1 toilet paper roll, or is it a bar? Yes. So we have, when we assign the barcode, what's distinguishable here? Space 1, space 2, space 3, space 4, space 5, 6, 7, all the way to 10. Yes, 10 spaces. The spaces are distinguishable. Which of those spaces are assigned to be toilet paper and which are assigned to be a bar? Do you see? So there are 10 nights and 2 destinies. You agree? The destiny is you are either becoming a toilet paper roll or a bar. Some destiny. Do you agree? Good. Here is the general situation, guys. So we have n. Notice, very important that you have to kind of keep in mind what's distinguishable. We have n indistinguishable objects. Yes. And m distinguishable destinies, right? So the objects are the toilet paper rolls, let's say, and m is the number of people. So each person is unique, it's different from another person. Right? So in that situation, if we distribute n identical objects among m distinguishable destinies, we have x1 plus x2 all the way to xm equal to n. So if that's the general situation, on the conveyor belt, we have to have n spaces allocated for the objects and m minus 1 spaces allocated for bars. Do you agree? We have the objects, the toilet paper rolls, and the bars. Since the bars are meant to divide the objects among the individuals, and we have m individuals, we have to divide into m segments. Yes, 1 bar divides to 2 segments, divides into 2 segments, 2 bars into 3 segments. So m minus 1. Do you see why minus 1, right, guys? So altogether we have n plus m minus 1 spaces. That's how many spaces we have. Each space is either a 0 or a 1. If it's a 0, that the space is assigned to hold an object, and if it's a 1, it's assigned to be a divider. Yes. So how many possibilities are there? Well, you can write it in this form. So it's n plus m minus 1, choose n, m minus 1, which means n of those spaces will be the objects, and n minus 1 of them will be the dividing bars. Those are spaces, right? And that's the same as saying n plus m minus 1, choose n. Or because as soon as I know what I chose, I also know, so that means choose n means choose out of those spaces what's assigned to be the object, the indistinguishable object. Then the remaining spaces obviously are bars, right? So I don't need to mention the other category because it's by default clear what is the other category. That's why you can have this notation when you have only 2 dragons, right? Multinomial coefficient is just the same as that combinatorial formula, right? N choose k, but multinomial is more useful when you have, it's a generalization. If you have 3 or more, then you have to specify the exact distribution. Or you can speak about the bars. Which spaces will be made to be bars? Yes, guys? Now, maybe I should send you or ask you to read the story. How many of you know the writer Hans Christian Andersen? I'm sure you must know him, right? Yes, very good. You should, guys, and if you do not know him, you definitely should read. It's very moving, right? You've all seen Disney's Little Mermaid, right? Have you? Did you like that movie? Little Mermaid. I did not like it at all. And why didn't I like it? It's because it's not Andersen's story. It's so meaningless, right? What happens in the Disney movie? The princess, this beautiful mermaid, because she's so pure of heart, she gets rewarded and she gets her prince. But that's not what true love is. It does not teach true love. You know what happened in The Little Mermaid, guys?
She turns into foam, right?
Exactly, guys. And if you love somebody, truly love somebody, you do that not for any reward. You do that to turn into foam. Yes? She loved somebody so very deeply and rescued. And the prince, he did not like her at all. He was very nice and wonderful, but he did not want to marry her. And he met a human girl that he loved, and she was not a bad person. She was not a witch. She was actually very nice, right? And the Little Mermaid, her destiny was to turn into foam, to die, to disappear, if the prince does not love her. That was the magic. And the mermaids came out to save her, and they sacrificed their hair, their beautiful hair, to give her a special dagger. And they say, stab this prince with the dagger, and you will become a mermaid again, and you will live for thousands of years. And the mermaid refused to do that. She sacrificed herself. And what happened to her? She turned into foam. And that's when you look into the water and you see the foam on the water. That's why you feel so sad. Yes, there is actually nice what, when, where questions about Hans Christian Andersen, if you ever want to listen to that question. He was a strange person. Yes. So here we will talk about a slightly different Andersen story. Do you all know the question about, do you know this little girl, the little match girl? Have you ever read that short story? Yes, you know it. It's very popular unless you are from here, I guess, right? I can see on your faces you have not read that story.
That's the one where she freezes to death?
Yes.
Okay.
Yes, that's the
I
one.
haven't read it, but that's kind of familiar.
That's my fairy tales, guys. That's the fairy tales I read. It helps me sleep at night. So here is what I thought when I read this story, right? So the matches that she is lighting to remember Christmas and that stuff, they are all identical, right? So just tell me, please, if you have, just a simple question, right? If you have M such poor little girls, and you have N matches, right, to give them, how many ways to distribute matches among those girls? You understand the question, right? We have N, and matches, I imagine they're the same, right? N matches, and each girl is allowed to receive 0, right? You might be not kind to a particular girl and give that one match girl 0 matches, and to another that you find more interesting, you give her more matches. Yes. So if that's the thing, how many ways to distribute the matches among the match girls? Yes. You mean something choose? I see what you're saying. Yes, Ryder. Very good. The answer to this question is the same, obviously, right? It's the same problem as with the toilet paper. So the answer is simply N plus M minus 1, right? We can have the matches, and in the supermarket, N minus 1 sticks. Altogether, N plus M minus 1 spaces on the conveyor belt, correct? And we need to pick N of those spaces to be assigned to be the matches. Good. Now a slightly different problem, guys. Now every girl has to get at least one match. Can you solve? Yes, just n. Do you see why I said just choose n, guys? Because n plus m minus 1 spaces, n of those spaces are assigned to be matches, and m minus 1 spaces are assigned to be the bars in the supermarket. They are just useful to partition. Good? Amazing. Now, I see two people left. I guess they don't like the mermaid story. So I changed of plan, guys. Now we are not going to allow any match girl to go without matches, right? Each has to get at least one match. How do you solve that now, please? Careful, guys, careful. All right, guys, let me tell you what you can do. Why not reduce it to a previously solved problem, no? I mean, you can just give the matches that each has to have, right? Each has to have a minimum of one match, right? So that means that we had initially n matches to distribute. We might as well suppose we have n minus m matches to distribute. Do you agree? Because m of those matches were already 1, 1, 1, 1 already given to each girl, and now I can give them 0 matches. Do you agree? So this is how many spaces we have, n minus m, and then we need to divide by additional, so it's plus m minus 1. Do you see why plus n minus 1? For the extra for the extra bars, we need more spaces. Yes. Choose, let's say, n minus m for the spaces to be occupied by matches. So altogether, the answer is n minus 1, choose n minus m. Let's see what somebody wrote, what was written there. So James, very close. Very close. The bottom is, it should be n minus m or something similar to it. Yes. Agreed?
Yeah, I agree.
Okay, let's see other solutions here. So you can also do this, guys. So I gave another argument. Here are the matches, and I only need to divide the spaces between them. So they are between matches n minus 1 spaces. Do you agree? And of those spaces, I need to pick m minus 1 spaces. So I can just as well write it as n minus 1, choose m minus 1, or which is the same, right? Because if it's, what's the multinomial coefficient? It's n minus 1, choose m minus 1 for the for those spaces, and n minus 1 minus this, which is n minus m. Yes, so which can be written either in this way, which is what you see here, or in that way, which you see over there.
Wait, I got a question. I'm sorry.
Go ahead, Jay.
Wait. So like, so you said out of each one, right? Out of each one, right? They have to have like one knife or something, right? So if I
One white.
wait, did I misread the question?
Well, I mean, I think you're assuming that knives are much more useful in the street than a match.
Oh, okay. I'm sorry. If all right, so if a person is supposed to have one match, right?
Mhm.
Shouldn't it be so right? Let's say, how would I? So let's say there's like no, that's gonna take too long. Matter of fact, can you just explain it? Can you just explain it?
Well, I'll try again.
Yeah.
Let's see. So there are several. I went briskly through another explanation, right? So the way I obtained my first answer, right? My first answer, I said n minus 1 chose n minus m, right? So I know this is the idea that I used there, right? I know how to solve this problem if I am allowed to give 0 matches to somebody, right? So we solve the initial problem with the barcode with zeros and ones with the assumption that somebody is allowed to get nothing at all, right? If you have 2 adjoint bars, that means the person to which the 2 adjoint bars correspond is getting nothing at all. Yes. But now I'm requiring each person to get, each girl to get at least 1 match. Yes, so I can deal with that by first giving them the match. So I give girl number 1 a match, 2 match, and so I gave them, before I started distributing, I gave each of them 1 match. Then I already satisfied the requirement that each has at least 1. Do you agree? Now,
okay,
I had m girls, right? M girls, so and n matches. So because I removed some matches, I now have n minus m matches. So I now have n minus m matches. And to divide those, I'm now allowed to use 0. I need to divide again into m girls. So I need addition. So I have n minus m spaces plus m minus 1 spaces for the total number of spaces. And out of those spaces, I need to pick spaces for the matches. Do you agree? If I pick spaces for the matches, it would be n minus m, because those are the matches that I have to distribute. So I have this, and that becomes n, because minus m plus m is 0, so it's n minus 1, choose n minus m. Or
because
yes,
okay,
yes.
so it would, so all right, so because you need to have the possibility of someone having 0 matches, right? That's why That's where you
Yes,
literally
yes,
put.
because I know how to
Okay.
solve. I know how to solve it
That's
when I have a little bit less heart, when I can give somebody nothing, right? So for then I just give everyone the requirement, and then I decide how to distribute whatever is left. And I can also do this. I can say n-1, the same number, and I can choose the bars. And if I choose the bars, I choose what? I choose m-1. Do you agree?
okay.
This is the space for the bars. I choose spaces that are made into bars. Yes? n-1, choose m-1. Good. And then I just outlined another strategy, which is just solving the problem from the very start without assumptions of any sort. I can just do away with this next requirement by doing that. Well, I have n matches, and now I am going to choose spaces between those matches. So first space I have to choose after first match, second space somewhere later, and as soon as I choose a space, that space will be dividing. So if I chose space 1, that means that this is a dividing line. If I choose space 3, this is a dividing line, right? So for instance, if I have 5 matches and only 3 girls, I need to choose 2 of the 4 spaces. You see, the spaces are between the matches. So I don't really go beyond this last match or before the first match, because those spaces are useless to me, right? So then I see that we have 5 minus 1 spaces, and of them I need to choose the number of the, what is it? If I said the distribution is into 3, I need to choose 3 minus 1. So if I have n matches, and I will have n minus 1 spaces, and out of them I will have to choose m minus 1 spaces to indicate partition. Yes, so that's another way of solving this problem. Good. And then there is the general approach, guys. Yes, should I cover it? Well, I mean, maybe a little, I suppose, right?
One more question.
Yes, please.
So like, why do I still have to include the possibility of 0 if everybody's getting at least 1?
Well, it depends what you use, right? So, I mean, I solved this question under 2 assumptions, right? So if I want to solve it from scratch with a new technique, then I can do this. This is my new technique. Again, I can re-explain it if it's not clear. But if I solve it with the old technique, in the old technique, I learned how to partition items where there is a possibility of someone getting 0 items. You agree? So that technique, that solution from the previous, basically with the toilet paper rolls, there was this possibility that somebody gets nothing. Correct?
Okay.
Right?
Yeah.
So if that's the method I'm using, this strategy is not going to work where everyone has to get something. So then I have to modify my problem so that I can, again, speak in terms of the previous solution. So the way I modified it is by giving each girl a match. So now I satisfy the requirement that each has at least 1, and then distributing the remainder and with the possibility of giving 0 from the remainder to somebody. Do you agree? Because I already satisfied the requirement that each has to have 1 match, and I don't need to solve it from scratch if I don't want to, right? And if I forget something, I can always do this. I can come up with lots of ways to solve a problem. So this is an example. Let's say, suppose I have 3 girls and 5 matches that I have to distribute, and each girl has to get at least 1 match. So then what I do is I can do this, a new procedure. I can place the matches on the floor, and after the first match, I mark space 1, space 2 after the second, space 3 after the third, and all the way to space 4. I don't go beyond, right? I have spaces fewer than matches. They are between them, yes? And then I would say, select 2 spaces. If you select 1 space, I cut the set into 2 parts. If I select 2 spaces, I cut the set into 3 parts, right? So because my goal is to cut the set into 3 parts, I have to select 3 spaces. Yes. So here's what happens here. If I select space 1 and space 3, that means that girl number 1 gets 1 match, girl number 2 gets 2 matches, and girl number 3 gets 2 matches. You agree? So that also corresponds to a solution, but now specifically to the problem where each girl has to get 1 match. And so then I can say choose four out of 4 spaces, choose 2. So it's 4 choose 2, and that is the possibility for division. Good.
Okay.
And in general, if I have n objects, I need n minus 1 spaces, and out of them I need to choose m minus 1 to partition into m parts. So it's n minus 1 choose m minus 1. That's directly solved. Right?
Wait, I'm sorry. When you
Yes.
said where you said from if the first girl gets 1 match, right? Shouldn't
Yeah.
she get technically 0?
Well, so that is, yes, that's another way to think of it. By the way, you can rearrange the equation. So if it's 1, it means it's adjusted to 0. That's yes, but you see, in the previous way I solved it, I gave each girl exactly 1 match, and now from the remaining matches I'm allowed to give 0. That's kind of the way I thought of it. We will talk about it after class if you want more of it. Actually, the after class is coming very soon, since I have about 3 minutes left. Yes. So yes, guys. So the general approach, I'm kind of getting lazy to talk about it. I kind of want you to figure it out. Suppose that different people have to get a different minimum. Do you agree? Different minimum. So that means in general, I hope you're not troubled by my symbols, right? In general, person xk has to get at least nk objects. Yes, and the total must sum to n. I can easily figure out how to do that by translating this equation into one where the solution is 0. You see, basically, if x1 has to be bigger than n1, x2 has to be bigger than or equal to n2, and onwards, and the sum must be n, then I can subtract from x1, I can subtract n. I decided to do it in terms of the solution. So I subtract n1 minus 1. So now this variable is bigger than or equal to 1. You agree? Because if this is bigger than x1 is bigger than or equal to n1, then this difference is bigger than or equal to 1. This difference is bigger than or equal to 1, and onwards. And then by subtracting n1 minus 1, n2 minus 1, and m minus 1 from each of them, I balance the equation by subtracting from the right side the same things. And I have this, which means that the number of solutions for this new equation is as written here. It's just this number minus 1, choose how many people we have here, m minus 1. That's the general solution. You can think about it and realize that must be the case. Here is a quick example. Let's just do a problem, guys. Last problem, please. And we will call it a day. All right, so how should I say that? Yes, you must pay them all, but at least it's a silly example, I don't know, but I kind of am embarrassed by it. But yes, I don't know, maybe I drank something when I wrote it. You must pay them all, but at least $10,000 this week, and your bank account is empty. You then recall the prize collection of silver spoons in your family. You own 2 spoons, your grandma has 6, and your parents have 4. If each spoon is worth $1,000 and you intend to pay your dues with the spoons, so how many ways to do that where you take as little as possible from your family? In other words, you commit your own spoons. That's all I mean by that, right? You use all your spoons, and then you decide how many more to use, right? So yeah. Let me give you slightly, this is a little worded a little weirdly. Let me give you this example, okay? So suppose that you have $20,000 to invest, okay? And you have to make investments in 1,000. Okay, and then you have option A, option B, option C, option D, 4 options, and each option has to have at least four, or at least let's say 2,000. Okay, how many possible investments can be made if you have to invest all of the money along A, B, C, or D? You understand my question, guys? So you have to place at least 2,000 in each of the accounts. It's a very, I'm just giving you a quick one since we're out of time, right? Just tell me in formula how many investment strategies are possible. And of course, lesson is over. So if you have to go and you cannot stay a little bit over time, then I wish you goodbye. Okay, guys. So this is the solution. Are you ready? So one way to do that is we can take 20, that 20,000. So 20 minus 2 times 4 or minus 8. So in other words, I already placed the investments in each account, right? And I have to place 2 4 times. So I have to place 8,000 investments. And then I divide into 4. So I add 3 spaces. And I choose among those spaces which spaces to be occupied, right? By what remains. So what I have is, so that would be 20 minus 8, which is 12. 12 plus 3 is 15, and that's 15 choose 3, which is the same thing naturally as 15 choose 12. Right? You agree? Yes, very good. So 15 choose 3. Those that say that. Oh, I'm gonna stop the recording, guys. If you have questions, something is not right away clear, you want more practice with this, stay with me. Otherwise, goodbye.